All right, section 1 in unit 4. It says Kyle is a photojournalist. Many of his photos are printed on photographic paper that is 6 inches long and 4 inches high. The ratio of length to height is expressed as 6 to 4. So ratio, I highlighted it in red because it's a key vocabulary word. A ratio is a fraction, or it's a relationship between two numbers. So any fraction that we have, we could call it a ratio. Now, ratio, you can write it as 6 to 4 with the word 2 there. You can also write a ratio as 6 with a colon and then a 4. That's still a 6 to 4 ratio right there. And you could write it as a fraction, 6 over 4. And the best thing to do would be to reduce it and write it as a 3 to 2 ratio. So any fraction that you see is a ratio of two numbers. So, and a lot of this will be a review for you guys, because you've seen ratios and proportions, especially in Algebra 1. But we do want to talk about ratio in relationship to some of the shapes that we're going to be talking about. So, kind of an example that I have right here, or a little thought one here, is it's because the mid-segment theorem, which we haven't talked about yet, but I do want to highlight the word mid-segment in a minute. The mid-segment theorem for trapezoids says that B, which is our line here in the middle, is the average of the bases. So it says write B as a ratio. Now that means just write B as a fraction. So in this case, B equals. Now how do I find the average of my two bases? This is a base in a trapezoid, and this is also a base in a trapezoid, because these are the two sides that are parallel to each other. So how do I find the average of two numbers? Add them together, divide by 2. Good. So you're going to have 12 plus 5. Those are my two bases. And since there's two bases, you're going to divide by 2. Anytime you want to find the average, you add up the numbers and you divide by how many numbers you're adding. So in this case, we're adding two numbers, so we're going to divide by 2. Now that's really not a ratio, technically, because there's a plus up here on the top. Our ratio would actually be 17 over 2 would be my ratio. Now I want to highlight for a second the word mid-segment. You're going to see mid-segments. They're not only in trapezoids. Triangles have mid-segments. Squares have mid-segments. Rectangles, parallelograms, they all have mid-segments. And in geometry, you're going to hopefully notice that what they call something is basically describing what it is. If they're calling it a mid-segment, kind of sounds like a middle segment, which is basically what it is. If you look at this letter B right here, you see this point right there where I'm making a dot at? That's a midpoint because I got two equal pieces. So this point has to be in the middle. And this point right over here has got to be a midpoint because it's got two equal pieces. So a mid-segment is a segment. It's a segment connecting midpoints. So when you connect two midpoints together, you're making a mid-segment. So that's how they do things in geometry. They always write down basically describing the word with what the word is. So since it's a mid-segment, it's a segment that connects midpoints. That was just a side note. The bottom part here says equal ratios are called a proportion. Anytime you have two equal fractions or two equal ratios, you have a proportion. This is a proportion. 1/2 equals 3/6. I know that these are two equal ratios. They would both reduce down to 1/2. So you could basically say 1/2 equals 1/2. That makes it a proportion because the two ratios are equal. Now on the next slide, we're going to look to see how to solve ratios. Solve proportions. And you've done it probably a million times already. But in geometry, we're going to definitely use it when we're with our shapes and our triangles. We're going to need to set up proportions and we're going to need to solve them. So two equal ratios, we call it a proportion. Again, if you miss any part of these or I'm going too fast or something, you can always rewatch. It'll be on there tonight before you watch 4.2 if you need to finish it. The solving proportions. Not a lot of things to write down, but there's a couple of things I want to highlight for you. Here is our proportions from the last slide. A over B equals C over D. To solve proportions, we use cross products. Now, what is product telling us to do? Multiply. It's telling us to multiply the diagonals here. So we're going to multiply the A times the D. That's going to be A times D right here. We're going to multiply B times C. That would be B times C. Those two multiplication problems are equal. In every proportion where you have two equal fractions, you're going to have your diagonals being the same when you multiply them. It works here. If you do 1 times 6, you get 6 right here. If you do 2 times 3, you also get 6. And we know 6 equals 6. So anytime you see a proportion, these diagonals are going to have the same product. Now, there are a few key vocabulary words. The word extremes and the word means. In geometry, we have something called a geometric mean. And it's based on the means in this proportion right here. Let me show you. Let me try to explain what an extreme is and what a mean is, or what the extremes are and what the means are. The extremes are what we call the outside numbers. If you go in order from A down to B, up to C, and down to D, if you go A, B, C, D, and that's in that order, then your first number and your last number were A and D. And those are called the extreme numbers. They're the outside numbers, the first and the last. So if you just go in alphabetical order, A, B, C, D, A and D are your first and last numbers. So we call those the extremes. B and C were the two middle numbers, the two inside numbers. We call those the means. Those are called the inside numbers. Extremes are your outside numbers, means are your inside numbers. And again, we'll be talking about geometric means later, but right now I just wanted to explain what the extremes were and what the means were. Now we do have a couple of properties that you'll want to write down. One of them is called the cross product property, which you've already used. Cross product property basically says that you could multiply the diagonals just like we did up here. So A times D equals B times C. And make sure that B and D are not 0. Why can't B or D equal a 0 down here? Because you cannot divide by 0. Remember we learned that in that proof that 2 plus 2 actually equals 4, and we thought 2 plus 2 equals 0. And you can't divide by 0 because if you do, weird things happen. So you can't have zeros for B and D. Yep. Yep. Okay, the inside numbers, if I was to list them in order, A, B, C, and D, what was the first number I listed? A, right? What was the last number I listed? D. So the first number was my first number. D was my last number. So those are what we call the two outside numbers. A, B, C, D. So A and D are outside. Yeah, exactly. And then B and C are the two inside numbers. Okay, reciprocal property. If you have A over B equals C over D, and you flip over the B over A, then you can also flip over the D over C. And here B and D cannot equal 0. And A and C really can't equal 0 either, because if A and C are 0 and you flip it over, then it's not going to work, because then A and C would be on the bottom. So we should also put A and C not equal to 0 as well. So you can't really have either one of them 0. Reciprocal property just works when you got two regular fractions and you're flipping them over. If you flip over one fraction, you have to flip over the other one. So that's called the reciprocal property. Again, these, like I said, these will be on there, so you can always pause it if you need to or go back to it or whatever. Okay, a couple of examples. It says, I can go back at the end. If 3 out of 5 plants from a distributor were diseased, then how many plants in a shipment of 250 should be diseased? So we're looking for a proportion that we could solve. It says 3 out of 15 plants. So 3 plants diseased out of 15 total plants that they send. That's a ratio, 3 to 15. I'm going to write it as a fraction because I want to make a proportion that I could solve. So 3 out of 15, I could also reduce that to make it a little easier on myself. If I reduce that, I could divide them by 3 and I could get 1/5. So a 1 to 5 ratio, 1 diseased plant for every 5 plants that they send me. So if I'm working at like Home Depot or something, and I'm the plant guy and they're sending me plants, I'm getting 1 diseased plant out of every 5. That's not a good ratio. You don't want a bunch of diseased plants in your store because you can't sell those. So you wouldn't want to buy from this person, obviously. But if this is the scale or the ratio, then how many plants, if they send me 200, would be diseased about? And that's where we're going to use our proportion and put X plants that are diseased out of 250 total plants. So X diseased, the number on top is our diseased plants, and the number on the bottom was the total. So we're going to multiply our diagonals. I'm going to multiply 5 times X first because I like to keep the X on my left side. So 5X equals 1 times 250. And that's just going to give me 250. And divide by 5 on both sides. So you're going to end up with X being 50 diseased plants. So there'd be about 50 plants that would have disease on them. That's just a way that we can use a proportion to solve it. That's why we look for some ratios. We look for patterns that we could use that will help us to predict. So we want to predict we should have about 50 diseased plants. That would be too many plants to be thrown away, so you don't really want that. Example 2 says Ivy spent $14 for gas to drive 350 miles. That's actually pretty good. $14 to go 350 miles. She must have a pretty good hybrid or an electric or car or something. That's pretty good. $14 for 350 miles. So that's actually a ratio that we could use. $14 for 350 miles. Now in my ratio, I put the dollars on top and the miles on the bottom. Could I have switched it around? Yeah, it's fine. And in my second one, I'd also need to switch it around. So that's the reciprocal property. If I switch one of them around, I got to switch the other one. At this rate, how much will it cost? So that's our X dollars. We don't know how many dollars it's going to cost. That's where we're going to put X. And to go 875 miles. Now, could we reduce this one first to make it a little easier on ourselves? Yeah. What number goes into 14 and 35? 7. You could actually divide by 7 and get a 2 over a 50. So that would reduce to a 2. That would reduce to a 50. Can I reduce 2 over 50? Yeah, I could actually make that a 1 over a 25. That would be my best and lowest scale right there, my lowest ratio, 1 to 25, equals X over 875. So I'm going to multiply my diagonals. I'm going to get 25X equals 875 miles. Divide by 25, and X would be $35. So $35 to go 875 miles would be pretty good. So the scale factor here. This is another key vocabulary term that I put in red, a scale factor. Scale factor is the reduced ratio. So in this example that I just did right here, what was the scale factor? What was the ratio that I reduced completely? Was it 14 over 350? Was it 2 over 50? Or was it 1 over 25? That's the scale factor. When you reduce it completely, that's where you get your scale factor at. We reduced that to 1 over 25. That became the scale factor that I could use for any other problem that I want to set up. I would still use my scale factor. Maps have scale factors. Like 1 centimeter on a map might be 1 mile in real life. It's always going to be reduced. Maybe it's 1 centimeter equals 50 feet or something on a blueprint. or 1 centimeter equals 10 feet or something. They're going to always have a reduced ratio for on a map that's got a scale factor. They're not going to put like 2 feet equals 4 centimeters or something. It's not going to have something that you can reduce. It'll be reduced if it's a scale factor. It will already be reduced. So that's just a couple of examples. There's 2 last examples that I want to use, and we want to use our scale factor on these last 2 examples. So let me go to my last couple examples. And it's talking about a building blueprint. Now, blueprints also have scale factors. The scale is 2 inches to 5 feet. So I'm going to write that down, 2 inches to 5 feet. Now, you may not want to write this whole problem. You might want to just write the scale. That might be something important to write on your paper. You might want to write down that he's looking for a cable drop that's 18 inches on the blueprint. So basically what he's got this building blueprint, and on the blueprint he's got a cable drop, or where he's got to drop cable down, and it's got to go down 18 inches on the blueprint. So he wants to be able to convert that to how many feet he actually needs to measure out and cut. Because on the blueprint it's 18 inches long, and 2 inches on a blueprint equals 5 feet. Now, is that reduced completely? Is 2 inches to 5 feet a good scale factor? Yeah, it is reduced. He wants to know if 18 inches is on the blueprint, how many feet would that be in real life? So that's our setup. Now we're going to multiply our diagonals. 2 times x would be 2x. This time I multiplied the extremes first, because again, I like the x on the left side. It's okay if the x is on the right side. It's not wrong. I like it here. And then 18 times 5 is 90. And then you divide by 2. And you get x would be 45 feet long. That's how much cable he'd actually have to measure and cut to actually drop the cable down in the building. He'd need 45 feet of cable. Now, do you think there's a way I could have solved this without cross-multiplying? In this case, does 2 go into 18 evenly? How many times? So I could have done 2 times 9, and how do I make equal fractions? Multiply the bottom one by the same number, you should get your answer here, which would be 45. So if it goes in evenly, you don't have to do your cross multiplying. If it goes in evenly. If it doesn't go in evenly, you need to do the cross multiplying. Let's switch it up here a little bit. If Rolando measures a distance of 42 feet at the building site, he measures 42 feet. How long should the segment be on the scale drawing? This time he wants to test the scale drawing to see if the scale is right. So he measures in the building, he measures 42 feet. Then he goes back to the scale drawing and measures it out. What should it be on the scale drawing? I'm going to give you about a minute or two to see if you can. Okay, so we got 42 feet. We got to use the same scale factor. 2 inches equals 5 feet. And this time I want to know how many inches, that's my x, over 42 feet. Now, you remember this last example where 45 feet was 18 inches? 42 feet is less than 45 feet. So our answer better be less than how much? If 45 feet was 18 inches, 42 feet better be less than what? 18 inches. Better be something less. Let's check it out. This time 5 doesn't go into 42, so we're just going to have to multiply. So we'll get 5x equals 84. Divide both sides by 5. And 5 goes into 84. 16 times 5 is 80. So it would be 16 4/5 or 16.8 inches. So 16.8 inches is less than 18, so it does work.